In this video, I'm going to give you a conceptual overview of how the snake in our game will be represented and how it will move. If you like, before continuing watching, have a think about how you might begin to implement this yourself. So in our version, we're going to represent the snake as a list of pairs of XY coordinates. So you can see here we have a list containing other lists, smaller lists, and each of those inner lists contains an X and a Y coordinate. The segments of the snake are currently lying all horizontally with Y coordinates of 0. And for this demonstration, consider the leftmost list item to be the tail and the rightmost to be the head. So here's that representation shown on a grid. So the green squares are the segments of the snake. Now the first thing we do is we make a copy of the head, and then we update the coordinates of that head to the new location and append it. So now there's 5 segments, so we need to remove the last segment so the snake doesn't change length. And then finally, turn everything back to the original colour. This is now the new position of the snake, ready to make another move. So again, we make a copy of the head. We update the position of the head and append it. Then we remove the last segment. And again, this is the new position. So let's look at that in just a little bit more detail. So to begin with, we have this list of lists. And by the way, lists of lists are quite common in Python, and they're no cause for concern. You can nest lists as deeply as you like. In this case, we only have one level of nesting, and this kind of list is often referred to as a 2D list. If you want a deep dive into Python 2D lists, I have a course on the subject in the LinkedIn library, which you may like to check out. So let's just go through that process again to make sure you understand it. So to move, we first create a new list item for the new head. This is looking a bit more at the code now rather than just the concept. So we create a new segment, which is the right-hand segment, and it's a copy of the existing right-hand segment. They must be copied, otherwise the original would be modified by the next step. So when we update it, we don't want to lose that original one. Okay, so new head is now the same coordinates as the old head of the snake. But then what we do is we increment the X coordinate in this example. So new head 0, this means the X coordinate of that new segment that we've created. We increment its X coordinate by 20. So now the coordinates of that segment are 80, 0. Okay, and we're just using plus equals here as a shorthand for new head 0 equals new head 0 plus 20. It's a very common shorthand to use. And then we append this new cell that we've created to the snake that we've already got, and it goes to the right hand side. So you can see now we have 5 items. So this new 80, 0 segment has been appended to the end. Okay, that's the right hand side, which we're calling the head. Okay, so we now have 5 segments, which has obviously changed the original length of the snake, so we don't want to do that. So what we then do is we pop the first element of the list, that's the 0, 0. It's the leftmost item, and then the snake will return to its original length. And that's the process, and we'll look in much more detail at the code in the next video. We're now going to look at how the basic snake movement can be implemented in Python. We're going to use stamps to make marks on the screen, as shown in a previous video. And what I have here is the stamp code from that previous video, but I've saved it with a new name, which is basic snake movement, and we're going to edit it so that it does what we want it to do for this chapter. So first of all, let's just make a few changes outside of the main movement function. I'm going to change that comment to something just a little bit more legible. Finished nicely. Okay, so we need something like that at the end of all of our turtle programs. Then we're going to add another constant, which is delay. And you saw this in a previous video when we were talking about animation in general. Let's do 400 for now. Obviously you can change this. This is milliseconds between frame updates. So this is going to be relatively slow, just so we can see what's happening. Then in terms of our screen, we're going to create a screen as usual. We're going to set it up using these constants, width and height. We'll give it a different name this time. This is now snake. It's the first program where we're actually doing snake. And let's give it a different background color. Let's give it pink. I've actually chosen this because it reminds me of a very old Atari game on a very old console. But that's just a personal preference for these retro things. You can choose whatever color you like. In fact, you know, the colors available in Turtle Graphics, pretty much anything you can think of will be available, and you can use hex codes as well. But another important thing we need to do is screen.tracer. And we discussed this in a previous video. This disables the automatic animation, giving us more or less full control of when we update the screen. Although having said that, some of the Turtle commands will automatically call a screen update in the background, so it doesn't give you full control, but it basically turns off animation. Okay, so turning off automatic animation. Now in terms of our stamper, we can have a square stamper, that's fine. The colour doesn't really matter, but let's not put a colour and then it'll be the default black, because that's the one I'm using for the rest of this game. Again, you can change to any colour you like there. I'm not going to change the shape size, in fact all of this can go, because this was relevant to the previous video. But I am going to do pen up. So that means it's not going to make marks as it moves. Okay, that's quite important, otherwise you get a very messy screen. Okay, so we've got a stamper turtle, its shape is square and it's not drawing on the screen. Okay, so now let's create our snake representation as the list of lists. And this is what we had on the slide in the previous video. We're going to call it snake, it's a global variable, and it's going to be a list of lists. The first pair is going to be 0, 0. Then we're going to have 20, 0. This is the initial position of the snake, or the segments of the snake. 40, 0. And 60, 0. Okay, so this is our representation of the snake in Python. Now we're going to draw the snake first off, and we're going to do that by using a for loop. So for segment in snake, we're going to do stamper.goto, and it's going to be the x coordinate and then the y coordinate. So that's segment 0 and segment 1. Okay, so 0 will be the x coordinate in each pair and segment 1 will be the y coordinate in each pair. So we go to the place we want to go to and then we do stamper.stamp. Let's just tidy that up and run it and see what we get. Okay, so you can see this actually draws the snake for the first time. It takes the list of lists of coordinate pairs and it turns them into stamps by moving to the location and then making a stamp. Okay, so that was drawing the snake for the first time. So that's a good start. However, for the snake movement, we need a movement function. And what we had before was a function, I think it was called move turtle. And we're going to call this one move snake. So def move snake. Doesn't take any arguments. Now the first thing we're going to do is we're going to clear all the existing stamps that have been made. So we do stamper dot clear stamps. That gets rid of all the stamps that the stamper has made. So that gets rid of the existing snake which has been drawn. Right, now we're going to do that business that we talked about on the slide. So we're going to create a new head segment. We're going to call it new head. Is going to be equal to the snake, and it's going to be the last segment in the list, and it's going to be a copy of it, because if we don't make a copy of it, then when we update it, it will actually change the original, which we don't want. Then new head, this is the x coordinate, new head 0 plus equals 20. That means we increment the x coordinate of this new head. Okay, and then we can actually append it. So add new head to snake body. We do that with snake.append the new head. Okay. Then we need to remove the last one, and we do that using snake.pop, and we're going to specify the 0th element of the list because we want to remove the left hand element. Okay, so we've now updated the representation of the snake internally. That's that list of lists, but we need to draw it. So again, draw snake. I'm just going to copy this because it's exactly the same commands for drawing the snake. However, this still won't be rendered. So if we want it to render, then we have to refresh the screen. So that's going to be screen.update. And then we need to do it lots of times. And we're going to do that by doing turtle.onTimer. So we're creating a timer whose function is move snake, which is the function we're currently defining. And we're going to do it with intervals of delay. Okay, so now when I run this, nothing happens. Now why is that? Okay, so nothing's happening, and that's because we haven't actually set the thing in motion. So we need to set the thing in motion by making that initial call to move snake. All subsequent calls will be handled by that timer that we created, but without that initial call the whole thing never gets to kick off. Okay, so then that should work now. Okay, and you can see it's moving its way along the screen. The snake disappears off screen before long, but this is a great start. We can add checks for border collisions and food collisions, etc., and also change the direction of the snake later on. We're now going to look at how to control the snake's direction. Controlling the snake's direction involves diving into the concept of events and event callback functions. Before getting into that though, we first need to create two new variables. One is a global variable called snake direction. The other is a Python dictionary containing offsets which determine how much the snake moves in each direction. So let's do that now. So let's put our offsets up here at the top, along with our constants, even though it's not technically a constant because it's a dictionary. Offsets equals a dictionary, and it's going to have up. It's going to give us an offset of 0,20 because that's plus 20 in the y direction. Down is going to give us an offset of 0 and minus 20 or negative 20. And left will give us an offset of negative 20, 0, 0 for the y, negative 20 for the x. And then right is going to give us an offset of 20, 0. Okay, so that's our offsets. Then this snake direction we're going to add outside of any functions. It's just going to be after we create the snake, and it's going to be snake direction. Initially it's going to be set to up, and this is a global variable. With that done, we can now talk about the event loop. You use event loops all the time when working with computers, although you may well not be aware of it. The basic idea is that a program listens for some kind of event to happen, such as a key press or a mouse click, and in response to particular events, specific actions are performed. In order to be able to listen, regular checks must be made to see if an event has happened, hence an event loop. You've used event loops in your Python Turtle graphics programs already. Do you remember turtle.done, for example? What this does is it tells Tkinter, which Turtle Graphics is built on, to wait for the user to click on the X on the window title bar to exit the program. The events we're interested in for our snake game are key presses. We want to be able to change the direction of the snake when the player presses an arrow key. So in order to make our program listen for events, we call listen on the screen object. So I'm going to create a new section of code. I'm going to call it event handlers. And to start with, we're just going to do screen.listen. Okay, this tells the screen to listen for events such as clicks and key presses. But now we need to talk about event callback functions. So an event callback function is the function which is specified as the required response to a particular event. So for example, in our game, if the player presses up, we want to call a function that changes the snake's direction to up, and likewise for the other directions. Now we're going to specify our callbacks in the following way. We're going to do screen.onKey. So when a key is pressed, we're going to call go up. That's the name of our function without the brackets because it's not a function call, it's a specification of which function to call. So go up, and that is when the up key is pressed, so that's up with a capital U. And similarly for the other ones, I did Control D to get that line in PyCharm. Go right for when the right key is pressed, and go down for when down is pressed, and go left for when left is pressed. Okay. So this is how we specify the callbacks for key press events. So on key, the function we want to call, and then the key that it responds to. Now we haven't defined these yet, go up, go right, go down and go left, so we're going to do that next. So def go up. So at this point we need our global variable snake direction, and we're making it global because we might be updating it, or we're using the global keyword because we might be updating the snake direction. As I said before, if you're only reading it, you don't need the global keyword. Now here we just want to put in an if statement so that we don't accidentally press the opposite direction to what we're going and create a collision. So we're going to rule out that possibility. So what I mean is if snake direction, let's use PyCharm's handy suggestions. If it doesn't equal down, then we can update the snake direction. Snake direction equals up. Okay. So if you think about it, you want to move the snake up, but you only want to do that if you're not going down. Okay, now the rest of these are very similar, so I'm just going to copy paste. And later on we'll look at a more efficient way of not having to have multiple functions for very similar behavior, but that comes later. So we've got go up, so that's going to be go right, and this is going to be go down, and this is going to be go left. Then let's just get all of these directions right now. So we've got go right, so if we're not going left, then we go right. And then for going down, if we're not going up, then we want to go down. And for go left, if we're not going right, then we go left. Okay, so that's the event callback functions. Now the only other change we need to make is inside of our move snake function. I'm not just going to update the x coordinate, which we did for our demonstration program, but we actually need to change both directions, okay, the x and the y coordinate. So I'm going to do new head 0 plus equals, and I'm going to get my offsets from the offsets dictionary. All right. So the x coordinate is going to be equal to the first one of those. So it's going to be plus equals offsets of the particular snake direction. And this is going to be the 0th one of those. And we'll do the other one, the new head 1. This means the y coordinate is going to be the offset for the particular snake direction, and that's going to be 1. So you might need to think about what's going on there a bit. But new head 0 and new head 1 are the xy coordinates of that new segment, and we're incrementing them by an amount specified in our offsets dictionary, which is up here, for the particular direction which the snake is heading in. Okay, let's tidy that all up and see what happens. And here it is. So the arrow keys now control the direction of the snake. Now, if you're not careful, it will disappear off screen and you might have trouble bringing it back on screen. Could even make an interesting little challenge of its own. There it is. You can change the speed as well, obviously. So if we want something a bit faster, let's have 100. So it's going to be a little bit more like a snake game now. Okay, long way to go, but this is the basics of snake movement and changing the snake direction. The heart of many games is the game loop. This is where essential game operations such as updating positions of game objects and checking for collisions occurs, continuously until the game ends. The game loop for the snake game needs to achieve the following. We need to clear the existing snake from the screen. We need to draw the snake in its new position, check for collisions with walls, self or food, and handle these appropriately, and also update the score. So far, our snake animation has been handled by the function move snake. The game loop needs to do the same, but has additional responsibilities as well. So we'll rename move snake to game loop and add some new functionality. Okay, so we've renamed that. Now in terms of collision detection, we want to check whether the snake has collided with either of the 4 walls, the top, bottom, left or right, whether it's collided with itself, and later on whether it's collided with an item of food as well. And we're going to do that by modifying the game loop function from what it was, and we're going to add these checks. So we're going to check collisions. And this is going to require a little bit of maths. So if the new head, that's what we just created, so this is exactly the same as it was in the last video, the creation of the new head, but now we're going to do a check based on that new head, right? So if new head is in the snake, okay, so that would be a snake with snake collision, or new head 0, that's the x coordinate of the new head, is less than negative the width. So if you think about it, the center of the coordinates is 0, 0, so half the width negative would be the left hand wall. So if it's less than that, width divided by 2, or the new head 0, so we're still talking about the x coordinate here, is greater than the width divided by 2, Remember, dividing by 2 because we're starting in the middle at 0, 0. So the width extends from half of the full width in the negative x direction to half of the full width in the positive x direction. And I'm running out of space here, so I'm going to go onto a new line by using this backslash and continue with OR. So this time new head 1, that's the y coordinate, is less than negative height divided by 2. So negative height divided by 2 is the bottom wall, or new head 1 is greater than height divided by 2. So that's all the wall collisions, and we've also covered the snake to snake collision with this new head in snake. Okay, so think about the maths for a bit, make sure you understand it. But if that's the case, what we're going to do is we're going to do turtle.by. Okay, that is just a way of closing the program, so ending the Turtle Graphics program. However, if there's no collision, so we now need an else. So if there's no collision, we just proceed as normal. So that's all this stuff we were doing. But let's just make sure we move it into the correct level of indentations. This is all going to happen if the else condition holds, not otherwise. So let's just tidy that up and run it. So that's all fine working, but when we hit the edge, the game ends. When we hit the edge, the game ends. Let's try and collide with ourselves. Yeah, you have to be pretty quick to do that. If you want to have a bit more of a chance of doing that, you can slow it down a bit. Let's have it at 500 milliseconds between frames. It's probably easier to crash. So you have to do it after a turn. Hang on, I need to think about this. So I have to do it after a turn and then back on itself quickly. There you go. So that's how you do collision detection for the walls and for the snake-to-snake collision. This version abruptly exits the program if a collision occurs. Later on we will change this so the game restarts instead. The collision code is fairly straightforward in principle, but it's worth spending some time making sure you understand how it works. We're checking first whether the new head is in the same location as an existing part of the snake, which would be a self-collision. Then we check the x and y coordinates of the new head against the boundaries of the screen, calculated from width and height.